So thank you very much for the possibility to present a recent result that was done by students in my research group mainly, on a topic that is related a lot to work that Nikolai has also done. And I hope to perhaps interest you a bit into looking into this a bit more. So this is a talk that is mainly observational, so it will not have equations, even though we all know that Nikolai usually likes to look at equations. And this is a beautiful example here from one of the visits that Rüdiger and I had to Moscow. And this is another one. And you also see that it's very difficult to have photos where Nikolai is not looking at either equations or data, which is, I think, also very characteristic and also a very good overall characteristic of researchers in general. So it shows the overall enthusiasm here. And some of the enthusiasm was also that I always felt very welcome in Moscow, even when I was still a grad student, and also felt very supported by all of our collaboration. And so when thinking about what should I be talking about here, there were various options available, and I decided to use a topic that has to do with eROSITA, because that really was for a very long time a beautiful joint collaboration between Russia and Germany before politics unfortunately made us to stop all of this. And eROSITA has resulted in a huge amount of very interesting data that are related to accretion flows and accretion physics in general. And I believe that this is a very nice result here that I'm going to present about the survey of ultraluminous sources in the eROSITA survey, or rather on the German part of the eROSITA survey. This is a work that includes a lot of people which are listed here. The primary driver behind all of this is Philipp Weber, a student of mine. The underlying papers here will be submitted in the next couple of weeks or so. So this work has not yet been published. So why are we interested in ultraluminous X-ray sources? And why is eROSITA such a very good instrument to do this? Ultraluminous sources are formally defined as point sources in X-ray images of other galaxies. They are somewhere, but not here in the center. We know that there are ULXs in the centers of galaxies, but since active galactic nuclei are also in the centers of galaxies, if you look for ULXs, you better don't look there. And there are sources who have extremely high luminosities in the super-Eddington luminosity regime of 10 to the 39 ergs per second or more. Many of the ULXs are transient, many of the ULXs are variable. You do not see the ULX here in this optical image. This is the same image now of this galaxy in the X-rays done with Chandra in this case. And you see that suddenly here at this location, there are two beautiful bright sources. And this is exactly how you find ULXs. You try to search for them in the X-rays, and you try to look for very bright sources that you can that you see in these galaxies. So what are ULXs? There are really two possible scenarios. One of them has been very surprising a few years ago when people started to look at them and detected pulsations in them. And these are very indicative of these objects to be neutron stars, but not neutron stars like Hercules X1 that Rüdiger presented, but neutron stars that have super Eddington accretion, because they're far too bright really for any standard Shakura-Sunyaev disk. You really need to go at the very, very high luminosity regime and understand their phenomenology there. And that's why we also have to observe them. However, the alternative, some subgroup of the ULXs are also much brighter than stellar mass black holes, but they're fainter than AGN. And an intriguing alternative for one of these subclasses is that they could also be intermediate mass black holes, which are somewhere between stellar type black holes and active galactic nuclei. So this is why these sources are so interesting. It is a mode of accretion that we can't access otherwise, and we also, to be honest, don't understand how they work. So the best way of going to understand these about 2,000 ULXs that we have, that we know right now in about 1,000 galaxies surrounding us, is to do some inventory of these sources. And this brings us to eROSITA. The reason for this and why eROSITA is such a good instrument for us to look for ULXs is that eROSITA performed an unbiased all-sky survey. You all know eROSITA was launched a few years ago now and then performed about 4 surveys of the overall X-ray sky. So contrary to all missions since ROSAT, eROSITA has really been looking at all of the sky and not only at selected sources. And that means that we can perform an unbiased search for ULXs rather than having to rely on people to look at the galaxy and then detect a point source there, right? And this observation, which are underlying most discoveries of ULXs, have the big problem. Typically, you select galaxies not because you want to search for ULX, but you select them because they're interesting for some other reason. And that is exactly where this bias comes in. So how do we do this for eROSITA? We know, well, ULXs are located in galaxies, so we need a galaxy catalog. And thankfully, since a few years, there's a very beautiful catalog called Hecate, the Heraklion Extragalactic Catalog, available to us, which essentially lists all of the 200,000 galaxies that are within 200 megaparsecs of us. The catalog is very useful for the work that I'm going to present because it also includes a lot of additional information about galaxies, from the optical luminosities, the mass of the galaxy, their star formation rates, and also things like the sizes, the so-called B25 region, so the border of the galaxy. And here's a nice example of what a galaxy does look like in Hecate. Well, this is an underlying image. For us, a galaxy just is this ellipse. So these are the 100,000 Hecate galaxies, which are located on the Western Galactic Hemisphere. So the part that we on in the German team of eROSITA have access to. Now, what you can see there is a combination of the in the distribution of the galaxies is a combination of large-scale structure. So you see these strands here where you have galaxies that are located really physically along a region in the universe. You see an exclusion zone here behind the Milky Way, where we know fewer galaxies because most of the light is absorbed. But you also see, for example, a change in the density of the galaxies here, and that is not real. Also, you see in the south, there are fewer galaxies in Hecate. And that just has to do with the fact that you have deeper surveys, optical surveys in this region and not down here. So we know that there are more galaxies down here, but we don't know where they are. So out of these about 100,000 galaxies, if you now look at all of the X-ray observations that we've done with pointed observatories, you find that about 30,000 galaxies have already been looked at. This might appear like a very large number, but this has to do with the fact that many galaxies are serendipitously in the field of view of observations or another object. And so the overall number of galaxies that we've looked at in the X-rays is formerly very high, but most of these have never really been understood. have never really been analyzed. Now, how do we go about to search for ultraluminous X-ray sources with eROSITA? Well, we take these 100,000 galaxies here, and then we look at the eROSITA data from all of these objects. And we then look for eROSITA detected point sources, which are located within the galaxy, meaning within this ellipse here. We decide that they are point sources which we can really detect with eROSITA, which means that their detection likelihood is high enough, so we have enough photons that we can really see the point source. They must obviously be located in the image of the galaxy, so within the D25. They must be away from the center of the galaxy, and we define here as an exclusion zone 12 arc seconds. And they must have a luminosity of larger than 10 to the 39 ergs per second, assuming that the point source is at the distance of the galaxy. And if we have enough counts, we then also characterize the spectrum of that point source. Now, these criteria are first criteria to find the sources, but the problem is there are other sources also which could look like ULXs, so-called contaminants, right? So, for example, you have supernova remnants in these galaxies, which could have a similar luminosity, but you could also have active galactic nuclei, which are farther away, but far more luminous, and might appear like a source that is in the ULX range if that point source was at the D25 region, right? So we have contamination, and we have to deal with that contamination. So, but before we do that, let's first take a quick look at one of these galaxies that illustrates some of the challenges if you want to do that really observationally. This is NGC 1824, 12 megaparsecs away. This is a very clear point source in this source, and this is a new ULX candidate that we detected there. And I guess everybody can notice this is a very bright source. Now, if you look on the optical image here, you see the location, right? It's far away here from the galaxy. It looks smack on the galaxy, and we're very sure that this is a proper object. What you also see is that galaxies are not always ellipses, and that the D25 region for this galaxy really does not characterize the shape of the galaxy. But unfortunately, there's not much we can do about that. So for us, all galaxies look like ellipses, even though most galaxies do not. But most sources are not as clear. And this, for example, here, you see this bright pixel here behind the red circle. That is more a typical type of an eROSITA ULX detection here, which has a fairly low detection likelihood. It still is in the galaxy here. It is in the outskirts. But with just the eROSITA data, we can't say much more than estimate its potential luminosity. But this is still very valuable because this gives us sources which we can then follow up in other observations. The problem now is that we have many of these faint sources, and statistics really doesn't work that well on deciding whether a source is a ULX or not. So we did some kind of a sociological experiment, and that sociological experiment was more or less that we gave images like the ones that I showed you before to a number of astronomers, really literally just forcing people at the observatory and elsewhere to look at these images and make a decision of whether what they see is a galaxy or not. And then to classify these sources, and each of our candidates, and there were hundreds of them, was looked at by at least 2 people. And what you see here now is the statistics on the detection likelihood. Is this a real source versus the probability that somebody of the people said, yes, this is a proper source or not. And what you're seeing is that this red structure here goes down. This is the number of sources where both people said, no, it's not a galaxy. And this is where at least a ULX, this is where at least one person said this. And so in the end, based on this visual inspection, we decided on a threshold above which we believe or do not believe a ULX. So this was quite interesting, right? This was a very good use of massively parallel computing with the brain rather than using a computer, and it was very useful. So we have two samples of ULX candidates, one that is in this regime and detection likelihoods between 10 and 20, where the sources can be kind of something else also, and a sample where we are very sure that these are ULXs. And to give an overview over the sample of sources, what we show here is the distance to the source and the luminosity. These two lines are the sensitivity, so sources which are fainter than this line here in a typical eROSITA survey, or so in a typical eROSITA survey would be difficult to find sources which are fainter at a given than this line here. Can only be found at the survey poles where we have a larger exposure. You see there are some sources that fall below these lines. This just has to do with regions in the sky where we have better observations. So what you see here is clearly we detect faint sources only nearby and more luminous sources only farther away. There are few very luminous sources nearby just because the volume that's covered is small and they are fairly rare. And you see blue and red colors here. The red colors here are new eROSITA candidates. So these are ULXs which have never been published in the literature. The blue ones are sources there are sources that are somewhere where we've never looked at before, so they're really completely new. We have 260 of these candidates, 245 are completely new. If you now look at the better sources, the ones with higher detection likelihood, you obviously have fewer sources, and we have 85 of these candidates, and 53 of them are new. So some have exposure with other instruments, so some are in galaxies that have been seen before, but we have not. But weren't published, and this typically has to do with the fact that we know that ULXs are luminous, are variable. So just so the fact that a source has not been detected before also tells you something, namely that these very luminous accretion flows are extremely variable and not just static. You may ask, okay, do we also detect ULXs that have previously been known? And the answer for this you find in this diagram down here. This is a distribution of the cataloged luminosities of ULXs of the 2000 ULXs. You see many of them are so faint that we would have not detected them with eROSITA, but there are enough there that we could detect them, and we detect a certain fraction of them. The ones that we don't detect, again, are ones that are variable. So this all works well together. And you might ask yourself, why do we care about finding 85 or so new ones, given that we know a few thousand of them? And the reason for this is the beauty of the eROSITA survey, and that is we really look at the whole sky and we can understand very well the survey sensitivity. So we can tell you for each source with very high statistical precision of whether we would or would not have found it. And this is illustrated here based on simulations that we did. So as a function of the short exposure time, this is the limiting flux above which, as a function of this detection likelihood, we would have seen a source or not. And that is really nice because this means we can compute for each galaxy in Hecate, for each of these 100,000 ones, what the limiting luminosity is for this source, for this galaxy. And that means we can correct for all of the observational biases. And that is far more difficult in other searches for ULXs. So this is shown here on the left-hand side. This is an exposure map that tells you the sensitivity and the detection likelihood, and this is the distance until up to which we would have detected ULXs. And so you see in the whole survey, there are 519 galaxies only where we would detect ULXs at a luminosity of 10 to the 39, but there are 100,000 where we would have detected the very, very luminous one. This just has to do with the fact that you can see brighter sources over larger distances, right? Now, this is one thing we can do, and I always spoke now about ULX candidates, and the reason for this is that we have contamination, so we have AGN and the supernova remnants and so on that I spoke about, but the really biggest contaminant is active galactic nuclei, and so we need to understand how many active galactic nuclei could appear like ULXs in our galaxies. And because we know the sensitivity for our detection in each given galaxy, we can now take the statistical distribution of AGN, the log n log s, and compute the probability that we would detect an AGN with a proper in the proper count rate range in the area of a given galaxy, and we can sum this up in a statistical sense, to estimate how many active galaxies we have as contaminants. And what we find is that we have a strong contamination. This is well known. This is also the case for other AGN, right? Of 30 to 50%. This sounds large, but the beauty is because we know the sensitivity so precisely, we can correct for that when doing statistical analyses on the behavior of ULXs. And for example, we can compute the luminosity function. So what is the number of sources brighter than a given luminosity in per galaxy? This is the first time that somebody has tried to do something like that with this precision. Typically, you find luminosity functions with some corrections, but doing this on a per galaxy basis with a large number of galaxies we probed is really something very amazing. So you find about 0.049 ULXs per galaxy. The distribution here is proportional to the luminosity to the minus 1.22. You see it's not turning over at the lower luminosities, indicating that we are complete. And you see that there is an indication that there might be a turnover in here. And that is something now that is a challenge for people who do accretion flows. And many of them are listening to this to really think about where this type of the luminosity function really comes from. So this is a beautiful example. Others have tried this before. Even cooler, in my opinion, is that since we know for each Hecate galaxy the type of the galaxy, and since we can correct for the AGN background, we can compute the fraction of the number of ULXs as a function of the host type of the galaxy. And what you see here, for example, is that we do detect in a statistically significant way also ULXs in early type galaxies, so type E and S naught. And these are galaxies where there is no recent star formation. So these are ULXs that are that cannot be in high mass X-ray binary systems because all high mass stars in these galaxies have already exploded. So these are ULXs which must be in low mass X-ray binaries. This is something that where there were indications already in previous work, for example, by Hugo Trenner, but we now have a much better statistics down here. And we also see a distribution here among the spiral galaxies, and you see this trend that towards later types, we have more of them. This has to do just with the structure of stars in there. But I would like to challenge people who like theory to think a bit more on how you can make ULXs in a low mass X-ray binary system. and how you can power them for such a long time that this type of a statistic that we now find with eROSITA can be reproduced in data. We have far more than that, but my time is over. So just to summarize, we find 245 weak UL axis, 53 very strong cases, which nobody has ever looked at before. There's a lot of evidence for variability there. If the slope in the XLF is real, we have evidence for two classes, HAMAS and GLOMAS X-ray binaries. We find in late-type galaxies that are more low luminosity UL axis, early ones in high luminosity ones. I did not show radial profiles, but the distribution of the galaxies over, of UL axis over the galaxy is what you expected. And the next steps for work, and hopefully we can also start working with people in theory again, is on the observational side to do the follow-up, but then also to understand far more the accretion physics at these highest mass accretion rates than what we do so far. And with this, I would like to conclude, and I would also wish you very much a happy birthday again, Nikolai. And may you always continue looking up to the stars and enjoy the stars and the beauty of the universe. Thank you.